let's solve some exercises related to the Jordan-Holder theorem. So here's problem 1. So I'll give you two composition series for a Z module, and you have to find refinements of that are equivalent for the composition series. The first one is Z contains 12Z, contains 36Z, contains 0, and the second one, so we'll call this number 1, and number 2 is Z contains 18Z, which contains 72Z, which contains 0. This is number 2. And these are composition series of Z modules. So you should pause your video and try to solve this yourself. You'll be using the argument that we used in the proof of Schreier's theorem. Okay, so let me solve this for you. So the idea is to refine each of these series using the other one. So firstly, let's refine 1 using 2. So refining 1 using 2 means that first we will take this part between Z and Z mod 12Z and find the terms in between this corresponding to this filtration. So what we do is first we take Z, and then we take Z intersect 18Z plus 12Z. This is something in between Z and Z mod 12Z. And the next thing in between Z and Z mod 12Z is Z intersect 72Z plus 12Z once again. And then the last thing is Z intersect 18Z plus 0, which is just Z intersect 18Z. So I'll write that on the next. Z intersect 0 plus 12Z, which is just 12Z. So I'll write that on the next slide. And now we go down and find terms between 12Z and 36Z, again using Z, 18Z and 72Z. So what I have to do is now I'll take 12Z intersect 18Z plus 36Z, and then I take 12Z intersect 72Z plus 36Z, and then I'll get here 36Z, and now 36Z intersect 18Z plus 0 containing 36Z intersect 72Z. And that finally contains 0. So now let's write down the actual terms of this series. We'll use two facts. One is that if you have AZ plus BZ, then this is the GCD of AB times Z. And if you have AZ intersect BZ, then this is the LCM of AB times Z. So here this denotes the LCM. Okay, so using those we can simplify these terms here. And so what we get, so first term is of course Z, then this is Z intersect 18Z, so we have to take the, that's just 18Z, 18Z plus 12Z, so that's the GCD of 12 and 18, which is 6Z. Okay, and now let's do it here. So this is this Z intersect 72Z is just 72Z, and now we have to take 72Z plus 12Z. So that's the GCD of 12 and 72, which is 12. So this is 12Z. And of course, that's still 12Z there. And so the next term, 12Z intersect 18Z. So that's the LCM of 12 and 18, which is, I believe, 36. So 36Z plus 36Z. So that's just 36Z because the GCD of 36 and 36 is still 36, and then we have 12z intersect 72z. Well, that's 72z, but 72z plus 36z is 36z. So we still have 36z. I won't write it again. And so again, 36z over here. Then here we have 36z intersect 18z, which is again 36z. And then finally 36z intersect 72z, which is 72z. So I'm not written the repeated terms because they will not really be needed to write down the common refinement. So this is the first, this is a refinement of 1. And now let's refine 2 using 1. So let's start again with z, and then we have, we're going to take plus 18z now. So we'll take z intersect 12z plus 18z. Then this contains z intersect 36z plus 18z. And now this contains, let's just go down a little more. So now this contains 18z itself, which in turn contains 18z intersect 12z plus, and the next term which is 72z, and then that contains 18z intersect 36z plus 72z, and then finally we will have the last row, which will be, so we will start with 72z, and then we'll filter it by the, so we'll take 72z intersect 12z, and that contains 72z intersect 36z. So that's the series we get, and now simplifying it, we get z contains, and here z intersect 12z is 12z, 12z plus 18z. So we have to look at the GCD of 12 and 18, which I believe is 6 again. And then here we have the 36z, 36 and 18, the GCD is 18. So now it's different from the previous series we had. And 18 intersect 12, so that's the LCM of 18 and 12, that is 36. 36 plus 72, so that's still 36z. And then here again we have 18 intersect 36, that's 36z plus 72z, that's still 36z, so that's the same. And then we have 72z, and you don't really, these are now both 72z, so the final step is 0. Let's just check that, so this refines 2. So let's just check that these are indeed equivalent by writing down the quotients. So I'll just write down the order of the quotient in each case. So that's because it's just going to be a cyclic group. So here it's 6, and then this is 2, and then so 6z mod 12z is a group of order 2, 12z mod 36z is a group of order 3, 36z mod 72z is again a group of order 2. So the quotients here are z mod 6z, z mod 2z, z mod 3z, and z mod 2z. Out here the quotients are z mod 6z, z mod 3z, z mod 2z, and z mod 2z. So this is just a slight permutation here. These 2 and 3 get interchanged. Okay, now let's come to problem 2. Let A be the matrix 0, 0, 1, 0, 1, 0, 1, 0, 0. And let M superscript A denote the RT module with the real numbers, R cubed, where Pt, a polynomial in Rt, acts on V, which I'll write as a column vector V1, V2, V3, belongs to R cubed by Pt V equals P of A. So this is the usual way in which we attach RT modules to matrices with entries in R. So the problem is, what is the length of MA? Okay, so just take a minute, pause the video, take a minute and try to solve it yourself. Otherwise, let me solve it for you. So you see, A has characteristic polynomial I guess t minus 1, it has one eigenvalue 1, and then it has two eigenvalues which are not real, plus or minus I. So it has characteristic polynomial t minus 1 times t squared plus 1, and these are both irreducible. So this is a factorization of the characteristic polynomial into irreducible factors, and so RT is isomorphic to RT mod t minus 1 plus RT mod t squared plus 1. And both these are simple because these polynomials are irreducible over R. So if we take our MA contains RT, we could take either one of them, is a Jordan-Holder series. And so length of MA is equal to 2. Okay, and a similar problem in the same vein, let's solve. So problem 3 is the same as problem 2, except we'll change the matrix A. And let's take A to be this matrix, just a 1 in the corner and zeros everywhere else. Okay, so pause the video and try to solve it. So here's the solution. So A has kernel spanned by two vectors, E2 and E3. So E2 is the vector, maybe I'll just write it down, 0, 1, 0, and E3 equals 0, 0, 1. This is easy to check. And so R cubed contains a span of E2, E3, contains span of E3, contains 0. This is certainly a composition series because the kernel is invariant, and of course also any subspace of the kernel is invariant for a linear operator. These quotients are one-dimensional over R, so they have to be simple because every submodule of an RT module is going to be an R subspace. So this is a Jordan-Holder series. And so since this is M0, M1, M2, M3, this has length 3. Therefore, MA has length equal to 3.